All right, guys. This is our last video on simple circuits, at least till we get to inductors. And that's going to be RC circuits. So I've drawn kind of a prototypical example. We have a resistor and a capacitor. They are in series. And then we have this weird sort of situation. So what I have is one wire connected to a terminal I call B, and I have another wire which is connected to a battery which is connected to terminal A, and I have a switch I call S, and you can imagine you could toggle between this. And if S is connected to A, then this branch B doesn't matter, and if it's connected to B, then the battery doesn't matter. So it's a way of just adjusting the circuit. Okay. So what I'm going to imagine is it starts out with a neutral capacitor, and there would be no current flow because everything's disconnected. And what we're going to imagine is that at time 0, you push the switch up to A. So you close, so at t equals 0, the current equals 0. That's the current through the resistor. And also, the charge on the capacitor would be 0 because it starts out neutral. And we close this, we connect to the battery. Okay, so we connect to the battery. So for this problem, we're going to, I'm going to erase this branch just so we don't get confused. And we just connect these up right here. Okay, so this is time 0. I connect it up. This is what I have. You're going to get a current start to flow. What actually happens is this. You should imagine there's a current which starts to flow, and it drops some positive charge on this side of the capacitor, which attracts negative charge, draws negative charges towards it, or pushes positive charges on around. But I should emphasize, no physical current actually jumps across the capacitor. If that happens, then you just melted your whole circuit. Okay. All right, so let's apply Kirchhoff's laws now across this situation. So I start here and I just go around. So I'm going to get, so I have a voltage here. So I have V minus IR. And then, you know, as you accumulate charge, it's hard to it doesn't want to keep adding more and more and more. So actually, as you cross the capacitor, you also have a minus. And now you need the formula for the voltage drop across the capacitor. Well, remember, for a capacitor, Q equals CV. Therefore, V on a capacitor is the charge on the capacitor divided by C. Now, strictly speaking, this is the current at the point of the resistor, and this is the charge at the point of the capacitor. But since there's nowhere else for it to go, then I know that the charge you gain on the capacitor is 1-to-1 with the current that passes through the resistor. Okay, so I have that little thing in the back of my mind. And then I get back to here and I get to 0. Now that's kind of different, a little different kind of equation. But it turns out most of you should be very familiar with this, because I can rewrite this to say, remember, I is equal to dq dt. So I can write this as dq dt times R plus Q over C equals V, or V for a constant voltage source. And if it was a sinusoidal one, you'd have that too. This is a differential equation. You get a differential equation for an RC circuit. It turns out it's a first order linear differential equation, pretty much one of the easiest ones possible. Okay, so let's, one thing you can do is kind of, we can divide everything by an R. And you'll notice on unit grounds, this combination R times C has units of time. RC is called the time constant. People call it the RC time constant. It's the parameter which characterizes the time scale over which the charge can change, either to grow or to shrink or to do anything. You measure the time it takes for changes to happen in this natural time scale, R times C. Remember that, the RC time constant. I think there's a sapling question where you need that. Okay. Tau equals RC. Okay, well, let's see. It's a differential equation. What are my boundary conditions? Well, I know that Q at time 0 equals 0 because the capacitor was not charged. And initially the current was 0, but then when I throw this through the switch, we got to be a little bit more careful. So let's be a little bit more careful about the initial conditions. I think I said things too quickly. So the minute you throw the switch, there's no charge here. If there's no charge on the capacitor, then there's no voltage drop across the capacitor. And if there's no voltage drop across the capacitor, in that very briefest of split seconds, at the very first moment, the capacitor actually just acts like a piece of wire for just a split second. So if that acts like a wire, then I think I said something wrong before. At the very beginning of this problem, when the charge is 0, in fact, there has to be a current. In fact, the current at time 0, just using this, so if this is like not even there, I find the current is equal to, it just looks like a simple resistor circuit. So I'd say the current is equal to the V divided by R. V equals IR. So I is V over R. Okay, so that would, sorry, I missed, when I said this was 0 before, that was before you throw the switch. After you throw the switch, the charge stays 0 just for a split second, but the current is pretty much immediately turned on. Okay, so notice, oh, and that's compatible with my differential equation, because if the charge on the capacitor is 0 at the beginning, then I is V divided by R. So at the beginning, I is V divided by R. Okay, so I don't know, maybe not everybody remembers how to solve differential equations. So what I'm going to do is just give you the answer, and we're going to verify it. So the answer to this differential equation is that the charge, as a function of time on the capacitor is equal to, well, let's see, it has to start out at 0, and it's a function which mixes derivatives and itself with this coefficient. So I'm going to guess, not really guessing, but I'm kind of feeling my way through it, that this is 1 minus e to the minus t over RC. And now I have to get the coefficients right. It's going to be C times V. So let's check. If that's correct, then the current is Q dot would equal minus minus plus equal plus e to the minus t over RC. And I would get times V over R. And if I add together Q dot with Q divided by RC, the C's cancel, and I end up with V over R. So that checks out. That's correct. If you don't see it, just make this guess, take this derivative, plug it into here, and you'll see that the left-hand side equals V over R. So what does that mean? Well, if you plot that function, Q is equal to C times V times 1 minus e to the minus t over RC. If you were to graph this, this is the charge on the capacitor. It starts at 0, and then it eventually becomes constant. If you wait forever and a day, wait forever, this exponential goes to 0, and you just get Q equals C times V. The current, on the other hand, which is given by the time derivative of the charge, just equals, has a graph which looks like this. Starts off not 0, and it falls off asymptotically approaching 0. So what's the interpretation of that? So this says that at the beginning you start with no charge, and you end up with CV. And over here we found that at the beginning the current equaled the voltage divided by R, and after a while it goes to 0. The logic of that is as follows. Let's go back to our circuit. So the logic is as follows. At the very beginning, there's no charge. And so the only significant component in the circuit is a resistor. And so sure enough, Ohm's law is there's V equals IR, so I is V divided by R at the beginning. But with time, you accumulate more and more charge on the capacitor. And eventually, the battery is not strong enough to add more and more and more charge. And eventually, you can't add any more to the capacitor. When that happens, the current goes to 0 because there's no more flow. You can't push any more on. So then the resistor effectively doesn't provide any resistance because there's no current flow. And then you get that the voltage drop across the capacitor would be, or sorry, that the charge would be Q equals C times V. And so what happens is initially the capacitor is not significant, and then eventually the resistor is not significant as the current fades away. That's how it works. I'll leave it to you to go through the same analysis, but you can imagine charging the capacitor and then disconnecting the battery. What's going to happen is the whole thing's going to unwind. The capacitor will discharge, releasing its charge or releasing current back through the resistor, and it'll neutralize. For a discharging capacitor, we find that the charge, it starts off initially with some initial charge, and then it decays. e to the minus t over RC. Again, RC gives you the characteristic time scale of variation, and you get an exponential decay. And then the current flows backwards. So if you work out Q dot to get the current, it'll come out with a minus sign. It'll be Q initial over RC times e to the minus t over RC. So compared to before, you'll get a relative minus sign on the current, because what happens is, as you do the charge up phase, maybe you get a bunch of plus charges on this side, but when you let it unwind, the flow counters and goes in the opposite direction. So if you want to see a discussion of the differential equation, stuff like that associated with this, look in the textbook. This is done in or anywhere online, people do this, so it's everywhere. RC is the characteristic time scale for variation when you have an RC circuit, a resistor capacitor circuit, and you get exponential decay and growth sorts of, well, it's not exponential growth, but you get this e to the minus t over RC as the characteristic function which controls your differential equation. Okay, so that, hold on 1 second, make sure I got everything covered that I wanted to say. Yeah, so that's everything I wanted to say about RC circuits and circuits in general at this point. Okay, our next topic will be magnetic fields.